Welcome back to NET Physics series. We'll be starting chapter number 9, which is of physical optics. So let's start our discussion with the topic of wavefronts. So wavefronts really are a locus of points. Any wavefront can be defined as a set of points where you have these points with same phase of vibrations. Now, wavefronts are capable of telling us where constructive or destructive interference will occur. So, if we have waves which are completely in phase with each other, that's where we'll see constructive interference. And where we have these wavefronts which are out of phase, perfectly out of phase, that's where you see destructive interference. Now, an example of a wavefront can be, for example, if I consider a point source, now waves that are coming out of this point source will be of this form. So let me try to draw it like this. Okay, so I think this is not gonna work. Let's do it like this. So it will be something like this. Now these are also called spherical wavefronts. So these lines that we have over here, these are the wavefronts visually. So this leads us to the next thing where we can discuss the multiple types of wavefronts. So we can have more than one type. This one was a spherical wavefront. So let's start by the spherical wavefronts, and as you can see in this diagram, these are really just a set of points which will determine the surface of a sphere. Then we have a cylindrical type of wavefronts, and if I were to draw these, you can draw them in multiple ways, but let's try to draw it on the surface of a cylinder. So you have waves that are coming out like this, right? And so you can see that these waves are really determining the surface of a cylinder. And hence these cylindrical wavefronts are really a set of points and they determine the surface of a cylinder. By the way, the source for the cylindrical wavefront has to be a line source, right? So here the source is a line source. And similarly, in the case of a spherical wavefront, we had a point source, which leads us to this type of wavefronts, which are plane wavefronts. And a plane wavefront is really you really have a plane from which you have these sets of lines or points just passing through like this, right? Now, in this case, this is the source, and the source is really the source is at infinity, right? So it's very long. Now you can get these plane wavefronts simply by having your point source, the point source that we talked about. You can place it at a very far distance. So for example, you could place it at the focal point of a converging lens. And if you place this thing at this focal point of converging lens, in that case you can obtain the plane waves from this point source. So it would be really placed at a very far away distance from the observer. Now we can define wavelength in this case as well, in the case of wavefronts, as it is the distance between these two consecutive wavefronts. The distance between these two consecutive wavefronts is one wavelength, right? And from here, you can also define the concept of rays. Now, rays are simply a line, really, which is normal to the wavefront. So if I draw it, it would be something like this from this point, and it is also normal really to the direction of motion of these wavefronts, which is in this case, it's in this direction. So then I can draw from every point on this wavefront, I can draw a ray that looks something like these. So these are all the rays. Again, rays are simply a line which is normal to the wavefront. Moving on, let's talk about the Huygens principle for waves, really. So first, let's understand the concept of original wavefronts and secondary wavefronts. So for example, if you consider this thing where you have points on this line. Now these points really are on the original wavefront. So this line is known as the original wavefront. So this is the wavefront that you have initially, and then we have, from all of these points, you can really draw a wavelet like thing around them, something that looks like this. Okay, so you have to forgive my drawing at this point, but something like this. Now these things, they are known as secondary wavelets or secondary wavefronts. Now these secondary wavelets give rise to a new wavefront which is a tangent to this point, these points on this secondary wavelet. So these give rise to this new wave front. So hopefully that clears the concept of a secondary wavelet. How can I have a new wavefront from my original wavefront with the help of the concept of secondary wavelets? So really in this thing, all these points that you see on this original wavefront, they are really acting as a source for these secondary spherical wavelets. And these secondary spherical wavelets are then further propagating forward in space with the speed of light. Now you can see that the position of the new wavefront that you see is really a tangent envelope to all of these secondary wavelets. And the radius of the hemisphere of these secondary wavelets, so this radius that we're talking about, this radius is really, well, because they're moving with speed of light, then the radius should be c times delta t, where c is the speed of light and delta t is the time that it takes for this spherical wavelet to be formed. So we can even discuss energies in these waves, really. And the if I consider a slit, something like this, where you have something like this, and you have wavefronts coming towards this slit. Okay, that's not a straight line, so let's draw a straight line, something like this, right? Now these wavefronts are moving in this direction. So what happens when they pass through the slit? It will produce these spherical wavelets, spherical wavefronts, something like this. And because they'll pass through this point as well, So they'll again, this is the distance between these two lines, really this distance is very small, so it's like a point source, and that's why we're having these spherical wave fronts coming out in this way, right? So it's something like this, right? So you'll have something like this where you can see there is interference as well going on. Now, this thing, we can draw a tangent, really, a normal line from all of these points, which we discussed already, that these things are called light rays, right? So, the line which is normal at all points to these wavefronts. Now, these are called rays. Now, the energy will also be flowing, so these wavefronts, they carry energy, and that energy that is flowing, it is flowing in the direction of these rays. So really understanding the idea of rays will also help you understand in which direction is my energy flowing. So, for example, consider if you had a homogeneous medium where every direction or every part of the medium is same, right? In that case, the energy of the transmitted wave that would be transmitted would be really equal in every directions, right? So the ray vectors would be really same in magnitudes. So it would be equal in every direction, and so the wavefront would remain spherical for a very long distance. Moving on, let's discuss quickly what is the Young's double slit experiment. Now, the Young's double slit experiment, you can consider you have these gratings, really, and so what happens over here is that these gratings are placed over here, and then you have a screen which is placed at some distance from these gratings. We'll define this distance from the gratings to the screen as d, right? So it is this distance. Let's call it capital D, and we can see that at the distance, these gratings are really, there is some separation uh, over here, so we'll define the distance between these two gratings as small d. Now, we'll also label this distance between, or really this gap that you can see, the gap of the slit or the slit width, we'll define it as some value a, right? Now, what happens is you can imagine the waves coming through these slits as we saw previously. So there would be like spherical wave fronts, they can come out of the slit, and there will be points where they'll be interfering, right? So if you imagine something like this, let me just quickly try to draw it. So you'll have something like this, and then you'll also have these things coming like this, right? Now you see clearly that there will be some points where you see that the wave fronts are interfering with each other. Now at these points you can have constructive interference, right? And you see at some places there are destructive interferences as well. Now we have studied these conditions for constructive and destructive interference in the previous chapter. So keeping those conditions in mind, we can really draw a line where we'll have, so for example, let's say that from this point to the screen, this point contributes something, and then this one also contributes something at this screen, really. So what's happening over here is we are considering these two lines to be the lines of constructive interference. So on the screen, you would really see something like bright and dark fringes, right? So wherever you see that this wave has a maximum amplitude, that's where you're seeing bright fringes, right? And where you see it's a lower minimum amplitude, that's where you'll see dark fringes. Now uh, we can define an angle theta from this line, right? So the angle theta is really, if I draw a perpendicular from this to this, something like this, then I can define the angle theta as this one, right? So this angle is really my angle theta. Now, if this is angle theta, then using geometry, I can also say that the you can really draw a line like this, a dotted line also coming to this point, because there will be this would be really something, a continuous like thing. And so the angle, this angle is also angle theta. Now, the path difference between for this wave that is you see over here, you can write that path difference as as d sine theta. You can use the geometry over here, and you can see how that becomes d sine theta, because we know that sine theta is really opposite side over the hypotenuse, and you can apply that over here, and you see that the path difference really is d sine theta. Now note that you'll see bright fringes, right? So the bright fringes on the screen corresponds to constructive interference. And remember, constructive interference was when you would have really the path difference we defined for constructive interference as n lambda. Remember, in the previous chapter, that was the condition for constructive interference. And for the dark fringe, you'll get dark fringes due to destructive interference. And the condition for destructive interference was 2n, the path difference, 2n plus 1 times lambda by 2. So that's when the waves are out of phase, and this is when the waves are in phase with each other. So now we can write down the equations, because we know path difference is defined as this. So this is generally a path difference. So in case of the bright fringes, I can define an equation for the bright fringe as d sine theta is equal to this thing, n lambda. So that's an equation that I have for the bright fringes. Then you have dark fringes, and the equation for the dark fringes is, well, you guessed it, it's d sine theta is equal to this thing. So that's 2n plus 1 times lambda by 2. So you can clearly see the first bright fringe. If I write down this distance from this center to this bright fringe, I can say that that's my y. So just using some of the trigonometry, we can write down this distance using this condition for maximum interference, which is a constructive interference really. I can say that my distance y, this distance, is equal to n lambda times this distance d, which is the distance between the slits and the screen, divided by the distance between these slits, that is small d. So that's my distance for the or you can say it's the position of the nth bright fringe, right? So this is the position of nth bright fringe. Similarly, you can also define the position for the mth, let's just use n, really doesn't matter. So position for nth dark fringe would be 2n plus 1, this thing, lambda by 2 times d by d. So this is the position of the nth dark fringe. And similarly, you can also then define wavelengths from these fringes. So for example, if I consider again, let's just write it over here. So for the bright case, bright fringes, the wavelength for the from the bright fringe is really this distance that we found for the bright fringe, which is y times d by m, or just use n times d, where this y is really again the position of the nth bright fringe, n is the number of whatever fringe that we're talking about, first, second, third, and small d, as we know that it's this distance, while capital D is the distance from these slits to the screen. And exactly then you can also define the wavelength from the dark fringes as 2y times d by 2m plus 1 times small d. So well, at this point you can also define something which is called the fringe width. And the fringe width is really the distance between the centers of two consecutive dark fringes or bright fringes, right? So for example, if I see this is my bright fringe and this is my bright fringe, then the fringe width is the distance between these two consecutive fringes. Now on a screen maybe it's something like this, so I'll just try to so let's say that this is my screen. It appears, so I'll draw my dark fringes with red color. So here I have, it's completely dark over here, and then with blue I'll draw my bright fringes, and here you see there is some brightness, and then again there is complete darkness over here, and then again there is light, so it's bright fringe, and then you have again darkness, and so this pattern really continues, right? So this continues like this. So the red is dark fringe and the blue one is the bright fringe. Now the distance between this bright fringe and this bright fringe is known as the fringe width, and fringe width can be defined as fw is equal to lambda times d divided by small d. Now this fringe width is not really always for the distance between bright fringes, it's also true, equally true really, for dark fringes as well. So if I were having these dark fringes, then this is also the fringe width, so it remains the same really. Now I can use this idea of the fringe width to really widen the interference fringe, so I can increase this distance, and that can be done by saying that the fringe width is proportional to lambda. So if I increase lambda, the wavelength increases, and hence the fringe width increases, and hence the interference fringe, this thing is really widened, so the distance increases, right? Similarly, I can also increase the distance between my gratings and the screen, and so the fringe width would increase. However, if I want to increase my fringe width, then in case of that small d, which was the distance between these two slits really, has to be decreased, and if this distance decreases, then the fringe width will increase. You can picture this if you shine a light, a torch really, between a gap that is very small. Then you can do this experiment as well. Moving on, let's talk about diffraction of light. Now consider that you have a wall over here, and you can say that it's something like this, and you're standing over here and you shine a light from a torch perhaps, right? So you shine a light, and the light will really go in such a direction that it bends across this path as well, right? So it will bend across this path, right? So it will be something like this. Now, so diffraction is really defined as the bending of light or spreading of light around a sharp edges. Now that's called diffraction, and it spreads these waves of light into geometrical shadow of an of this obstacle. So in this case, it could be this wall, right? And it distributes the light intensity, which will result in fringes. Some of them could be dark and some of them could be bright. So here you can see some of the differences that are listed between interference and diffraction. So we know that in interference, we have superposition of only some of the wavelets, and only that can tell you about the interference of the waves. So it can be constructive or destructive. While in diffraction, the superposition of a very big number of secondary wavelets are involved. So in diffraction, you consider many of these secondary wavelets, and when these secondary wavelets are superimposing each other, so that forms a diffraction pattern. Now in interference, the number of fringes, or you can say these fringes, all of the fringes, they have equal size. However, in diffraction, the fringes will start becoming smaller and smaller as they move, as the source really is moving away, right? So the source could be any diffracting object really. And interference fringes are equally spaced. So the spacing between the fringes in interference is also equal. Remember, we talked about the fringe width. But in diffraction, fringes will become narrow as the distance from diffracting object increases. So as you move further and further away from this diffracting object, so you move behind and then you shine a light, then the diffraction fringes would become smaller and smaller. And then we have an interference that the points of destructive interference are perfectly dark, right? So there you cannot see anything, so they have completely annihilated and destructively, right? So there is no light at that point. While in the points of while in diffraction, the points of minimum intensity are not perfectly dark, so it's not entirely completely black in diffraction, where you see minimum intensities of light. So here you can see an equation. This is known as the diffraction equation sometimes, and this equation is normally derived from the narrow slit diffraction, and it's also known as the condition for the nth order minima for diffraction. Here this d is really the width of the slit, while n can be any integer. It could be 1, 2, 3, 4, which is really telling you about the first order, second order, third order, fourth order of diffraction. So it's specifying the order of diffraction. Lambda is obviously the wavelength of the light which is diffracting. Now let's discuss diffraction gratings really. And diffraction grating is this, you can see it's a multi-slit arrangement of parallelly spaced, but these gratings are spaced equally, right? So the distance is equal between these slits. Now suppose that you have a monochromatic light and it is directed at the grating, which is parallel to its axes, as you can see over here, right? So the distance between these two successive slits is so for example from here, let me use another color, let's use red. So this distance is d, as we saw before. So now you can see from here the diffraction pattern on the screen. And this diffraction pattern on the screen is really a result of all of these combined effects of diffraction and interferences. As you can see that these rays are interfering at some points. Now, every slit is going to produce diffraction, and the diffracted beams in turn interfere with each other, as you can see, and they will produce this pattern on the screen. Now, the path difference between waves from any two adjacent slits, right, it can be found by simply, if I drop a perpendicular line like this, right, this line you can see between these two parallel waves. Now, by geometry, you can use geometry and find this path difference to be d sine theta. Now, if the path difference is equal to one wavelength or any integral multiple of, so that was n lambda, right, of this wavelength, then the waves from all the slits will be in phase with each other, and so you'll see the bright light on the screen. Now, that is, remember, a condition for constructive interference. However, you could also have a condition of destructive interferences where this path length is equal to the n plus half over times lambda by 2, and then you would have destructive interferences. Now, the condition for maxima in the interference pattern would be then defined as this thing, d sine theta is equal to n lambda. So this is the condition for maximum or maxima where in your interference pattern. Now, because this distance between these two slits is really small for diffraction grating, so a beam of monochromatic light passing through a diffraction grating will split into very narrow maxima at very large angles, as you can see over here, right? So the angles are very high. Now, this thing that you see over here, the spot that you see over here, I can draw this something like, so you have a ray of light coming like this, you have a grating which is something like this. So you'll have partly it would pass straight, some of it will go something like this, and then it will, so this is where we see diffraction really happening. And so this is known as the 0th order diffraction. This is the first order diffraction, and this is the second order diffraction. Now, exactly opposite or in the mirror image of that is also, this is first order diffraction, this is second order diffraction, right? And so you could have then you could have third, fourth, and so on. Now, as you can see that there are so many slits over here, multiple slits, you can find the distance between the two slits, and that distance between two slits, if I go down over here, let me write it, it's called the grating element. Grating element is the distance between the two slits, and it's defined as d equals 1 by capital N. Now, N over here is the number of lines that you can see in 1 unit length. And this equation is known as the grating equation, and over here N is really the order of diffraction pattern, right? So this is 0, something like this. So if n is 0, then you would be talking about this one. If n is 1, then we'd be talking about this ray, and so on, right? Moreover, we can talk about something or define something that is called the resolving power of the grating. And resolving power of the grating is the ability to separate two wavelengths of light. Two wavelengths of light. Now, this resolving power of the grating is given as you can write it as, let's just give it a name, R P, resolving power, and it is defined as lambda by delta lambda. Now this thing is known as the resolving power. So it's, you can see that it is really the ability to separate two wavelengths of light. So here we have some lambda, and this is the difference between those two wavelengths, and this is equal to n times n, where n is the order of diffraction and n is the number of lines on this grating. And again, delta lambda is simply the difference between those two wavelengths which are to be resolved by the grating, really separated by the grating. Now we can quickly talk about X-rays and really the diffraction of X-rays, and these diffraction of X-rays are defined by what's called the Bragg's law, and Bragg's law is just given by 2 times d sine theta is equal to n lambda. Now d is the spacing of the lattice. So for example, you can see something like this. So you have a plane, and in this plane you have multiple atoms, right? And then you can have another plane below this one, and so you can consider you have sets of planes like this. Now what happens is you throw an X-ray, it interacts with the atom and it bounces back. Part of it will go back down, right? And it will again bounce back from another atom, and so it keeps going down, and the same thing keeps happening. Now d is this spacing between these two planes, and theta is the angle of diffraction. Now solid crystals behave as very good natural diffraction gratings because of these planes that you can see over here. So you can throw some ultraviolet light on them, and it is diffracted by the layers of atoms which should be on this plane, right? Now the interatomic layer distance, which is the distance between these two atoms, really is known as the lattice constant. Now you can use this X-rays and the diffraction of these X-rays to compare the relative intensities of the bright and dark spots that are formed on the screen. And with those spots you can understand the structure of the solid, really the crystal structure of the solid. Moving on, we can talk about polarization. So really, when you confine your electric vectors of light into a single plane is defined as polarization. So for example, you have a light which is in every direction, right? So something like this. Now I can use a polarizer. It's a filter really, and it produces polarizations, and it's called a polarizer. And if I place that polarizer, what I can achieve is, for example, maybe I want to polarize my light, or in other words confine it to this plane where only the light that is in this direction passes through. So what I've done is I've taken my light which was pointing in all the directions, and I have confined it to this plane where it is only allowed now to be in this direction. So the final result would be the light that is in this particular direction. So really a wave that was coming in all of these directions is now polarized like this, and this is known as a vertically polarized light, and the polarizer that does this thing is known as the vertical polarizer. You can also have another type of polarizer, which is the horizontal polarizer, and you can use the combinations of these polarizers to really play around with this light. So if I used let's say I used a polarizer that was something like this. So I'm just drawing a polarizer right now, and it is only going to polarize light. It is only going to allow the light that is in this direction to pass through. So this would really give me a light that is polarized in this direction only. Then you can use the combination of vertical and a horizontal polarizer to allow a light which is diagonally polarized. Now, this polarizer really absorbs all the magnetic vectors and the randomly oriented electric vectors as well. And it will only leave those vectors untouched, really, those which are in this particular plane, whichever plane polarizer I am using. In fact, this polarization principle is really what establishes that light is a transverse wave. And so a polarization can only be applied to electromagnetic waves, and the reason for that is because the electromagnetic waves are waves which are like this, and the magnetic waves are perpendicular to these. So let's just let me just use this thing. So this blue color is really my magnetic waves if this is my electric waves. And you can see clearly that the electric and magnetic wave vectors, so if I draw a vector for electric, it's like this, and for magnetic it's like this, right? So really these two wave vectors are perpendicular to each other, and they're also perpendicular to this direction of motion because they're moving in this direction, right? So they're perpendicular, all the directions are really perpendicular, and hence we can use a polarizer to polarize this light in different directions. I can calculate the intensities also of these polarized lights by using the Malus law. Ignore my pronunciation of the name, but the law is given as intensity is equal to the original intensity of the wave times cos squared theta, where theta is the angle of polarization and this new intensity is the intensity of the polarized light, where I naught is the intensity of the incident light. Now you can obtain polarization by multiple ways. You can have it by reflection, you can have it by scattering of light as well. Finally, there are multiple uses of polarization as well. Some of them include you can use the polarizer to really enhance any effects of clouds and sky in your photograph, or you could also really control glares of light. So for example, if you're driving a vehicle at night time, you can control the glare of your headlights in night driving.